This is Professor Gao in Fresno, California. Let's solve a physics problem. The question is, how many logs 3 meter long and 18 centimeters in diameter are needed to just barely float a 2,500 kilogram car? The density of the wood are given. So this is a classic application of Archimedes' principle. So let's review the core physics concepts relevant to this problem first. So Archimedes principle says any object submerged fully or partially in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. So this force is given by density of the fluid, volume of the displaced fluid times g, which is gravity acceleration, which is about 9.8 meter per second squared. Notice that the displaced volume can never exceed the object's own volume. Therefore, the volume of the displaced fluid must be less or at most equal to the volume of the object. Also remember the density is defined as mass over volume of the object. So now let's discuss how does a rock think? Why does a rock think? So let me start a new whiteboard. Let's draw how many forces are acting on the rock midway under a swimming pool. So there are two forces acting on the rock. The gravitational force going downward is m of the rock times g, which is density of the rock times volume of the rock times g. The upper bound force is given by the density of the water, volume of the rock times g. Because the density of rock is much heavier than the density of water, therefore the gravitational force is much bigger than the buoyant force going up. The rock sinks to the bottom of the swimming pool. Now let's discuss why does wood floats. So again, there are two forces acting on the wood. The downward gravitational force is mass of the wood times g. Therefore, this is the density of the wood times volume of the wood times g. The buoyant force is given by the density of water times volume of wood times g, because the wood is totally submerged in the water. Because the density of the wood is less than the density of water, the force going down, gravitational force, is less than buoyant force. So therefore, the wood rises to the surface of the swimming pool and floats. Now let's return to the original problem and consider one log floating on water. Let me start a new whiteboard. So consider one log floating on water. As additional weight is placed on top of the log, it sinks deeper into the water. Eventually, the added weight reaches a critical value where the log just barely floats. At this point, the entire log is submerged, but it is still floating in equilibrium. So let's now simplify the original question to how much mass can one log support when it's just barely floating on water? Once we know the maximum load that one log can carry, finding the number of logs needed to float a 2,500 kilogram car is straightforward. So before calculating anything, do you think one log can hold 20 kilogram, 200 kilogram, or 2,000 kilogram? So let's draw the free body diagram. How many forces are acting on the log? There's a load on top of the place on top of the log. There are three forces as shown on the free body diagram. So let me write this on the whiteboard. So we have the downward weight of the log, which is mass of the log times g, or density of the log, volume of the log times g. We also have the weight of the load going downward, which is mg. We also have the bond force going up, which is density of water times volume of the log times g. Because the log is floating in equilibrium, therefore the sum of the forces going downward, which is weight of the log plus the weight of the load, must equal to the bond force going up. Substituting the force expressions gives us equation number one. Let me write this on the whiteboard. This is the only physics equation we need to solve for mass M. You notice every item has G. We can cancel G and rewrite equation number two to have equation number one to get equation number two. So all the quantities on the right-hand side of this equation are known. So now all the physics is finished. The rest is simply calculation. Keep in mind to use the correct units and keep in mind the density of water, density of wood are all given. The volume of the log, because log is a cylinder, the volume of the log is given by pi r squared L. L is the length of the log. Let me start a new whiteboard. We can find the volume of the log is 0.0763 meter cubed. So plug in those into equation number two, we can find the maximum load supported by one log. And this is 21.37 kilogram. So this means each log can support an additional load of only 21.37 kilogram before becoming completely submerged. Then we can decide the total number of logs needed to float a 2,500 kilogram car. Because the number of logs times the maximum load per log must equal to the mass of the car, you can find the number of logs needed is 116.97. Since we cannot use a fraction of the log, we round up to 117. So the final answer is, let me write this on the whiteboard. Because each log can support about 21.4 kilogram of additional load, when it just barely floats, we need 117 logs, 3 meter long and 18 centimeter in diameter, to just barely float a 2,500 kilogram car. I hope this explanation helps you understand not only how to solve this problem, but also why Archimedes' principle works. If you have any questions or comments, please feel free to contact me.